Okay, part C is, given that g of 0 equals -5, we want to write an equation for the tangent line to g, where the point, or at the point where x equals 0. So now I'm again writing a tangent line. That means I'm going to need a point, and I'm going to need a slope. So the point is already given to us. It's 0, -5. The slope is what we're going to need, and that will be g prime of 0. So that means we've got to go back to our definition of g. So way up at the top, we were told that g prime was e to the -x over 2 times 4f of x's minus 2f prime of x's for all x's. So I need the slope at 0. That means I'm going to plug 0 in, and I'll get e to the -0 over 2 times a 4f of 0 minus a 2f prime of 0. Well, e to the 0 is just a 1. F of 0, if we went back up to the top, we can see that f of 0 is 2, and then f prime of 0 is a 4. So if I put that all together, I have an 8 minus an 8. That gives me a 0. So the line will now be y equals 0 times x minus 0 minus 5. Or you could just write y equals -5. Either of those would work. If we look at the breakdown, you get 1 point for recognizing that that point was given to us. You get another point for determining that g prime of 0 is 0, and you get your final point for the equation of the line. So this section was worth 3 points. Now if we look at part D, we want to show that the second derivative is equal to this. So we're going to be looking to see whether or not you can take the derivative of the first derivative that was given. So the second derivative is going to involve the product rule, because I have two things multiplied. So I will have the first thing, which is e to the -x over 2, and now I need to multiply by the derivative of this. So I'll move through the constant, hit the f. The derivative of f is f prime. Then I'll move through the negative, move through the constant, and hit the f prime. The derivative of the f prime is an f double prime. So here's the first times the derivative of my second. Now I need to add the second times the derivative of the first. So the derivative of the first will be e to the -x over 2 times a -1/2. We did the chain rule on that. Our goal is to show that this is equivalent to this. So if we look here, we can see that there's an e to the -1/2 factored out. So I'm going to pull this and this out and leave what's left over inside. So that would be an e to the -x over 2 times, inside I'm going to have a 4f prime minus a 2f double prime plus a -1/2 times that 4 is a -2f of x's, and a -1/2 times a -2 gives me plus an f prime of x. So now if I combine my like terms, I can see that I have, and put them in descending order, I'll get an e to the -x over 2. I'll have the -2f of x coming first. Then I've got 4f primes plus another f prime gives me 5f primes. And then I have a -2f double prime. Notice that we got the same thing that we were trying to get. So the point breakdown on this is, can you take the derivative and then show it to me? So 1 point for that. The final point says, does g have a local minimum at x equals 0? Now remember when I taught you that second derivative test for maxes and mins, I promised you that on the test I would force you to use it. So when we want to find local mins or justify the existence of local mins, there are two ways that we can do it. We can use the first derivative test or we can use the second derivative test. The first derivative test would require that at 0, g prime is 0. So if we look up here, we can see, yep, g prime is 0. We got that from part C. But then to do the first derivative test, we would also have to know what's happening with g prime to the left and right of 0. Well, looking at our definition of g prime, we don't have any values of f when x is less than 0. We don't have any values of f prime when x is less than 0, nor do we have those when x is greater than 0. Because of that, we can't compute the sign of g prime to the left of 0 or to the right of 0. So the first derivative test is not going to work. That means we have to use the second derivative test. The second derivative test involves information about the second derivative at 0. Well, fortunately, they kind of led us toward that by having us find the second derivative in part D. So if I plug in 0 here, I'm going to get e to the 0 times a negative 2f of 0 plus a 5f prime of 0 minus a 2f double prime of 0. And guess what? We know all of that information. E to the 0 is 1, f of 0 was 2, f prime of 0 was 4, and f double prime of 0 was 0. If I put that all together, I get a negative 4 plus a 20 minus a 0 gives me a positive 16. So what that's telling us is that I had a horizontal tangent and then I had positive concavity. Because of that, we can use the second derivative test to show that we have a minimum at x equals 0. So the final justification is we will write g has a local min, or yes, g has a local min at x equals 0 because g prime of 0 was 0 and g double prime of 0 was positive. So point breakdown on E, we get 1 point for saying yes, and we get another point for using that second derivative test to explain why. And we're done.